So, hello everybody. We are at the top of the hour. I think we can start. No? Okay. Welcome to our talk about outscaling Kubernetes. Let's start right away with the two of us. I'm Matthias. And I'm Andreas. And we're both working for Deutsche Telekom. And before Andre gives you the details about how we outscaled Kubernetes, I will shortly introduce the context and the motivation why we did it. So being a telco operator, we looked into networking and specifically into networking with non-terrestrial networks. Can you see the slide? Okay, good. These networks have the property that the nodes are moving, they are changing their positions. And today's routing algorithms are not designed for that, so we knew we had to test them and potentially also develop new ones. And as we later found out, this applies also to other modern networks like vehicle-to-vehicle communication and mesh networks, ad hoc networks, and so on. So the problem was, how do we test them? We need a lab platform because these networks are too complicated to analyze them analytically or theoretically. To look into a simple example for a basic building block of that, we have a ground station, we have a satellite. The satellite and the ground station communicate, but only if the satellite is in view. So the link, this test platform, has to block communication between two interfaces depending on where the nodes are. When the satellite comes up over the horizon, the link has to be allowed. If it's below the horizon, it has to be blocked. While it travels across the sky, the link properties have to be adapted. To implement that, we need two things. We need two containers that run the software that will be later in the satellite or in the ground station, and we need to adapt the link characteristics, and we need to do that in different layers, because if we would let the satellite or the software running in the satellite decide about its link conditions, we would create a validation problem. So we need a platform that controls the network, and we need the containers to run the software which later runs in the satellites. Now for the scaling, this was one link. If we look at the constellation, that's a very simple constellation, that's a GPS constellation. And what you can see clearly is that the ground station rotates, during its rotation with the Earth, connects to changing subsets of satellites, which means we cannot carve out subsections of the network. We have to emulate a complete network. Now how big is that? Depending on the use case, we're talking about 1 to several thousand or even tens of thousands of ground stations, depending on what we use them for. For the satellites, smallest useful constellation is 3 geostationary satellites, but most constellations consists of tens or hundreds of satellites. Some, in case of SpaceX, for example, even thousands of satellites. They're currently around 8,000. So we have to scale the platform to that, to a degree that we can emulate the whole network as one. We decided early on that we would use the containers because VMs are too heavy, bring too much overhead, and we decided that we use filter tables and traffic control to emulate the link layer. We are relatively confident that the TC or traffic control and network filter tables scale, but we were not really confident that Kubernetes scales because there were no reported or documented installations that scale to that degree. So what do we need? What are the requirements for that scaling in that phase of the project? And that's the few of the key requirements. The first two are straightforward. First, obviously, we have to find out how can we scale? What's the density? How many containers can we support per cluster and per network node? And how many interfaces can they have? Because satellites can also create interfaces in space between them, so-called inter-satellite links. The third one is, in one aspect, also obvious. We have to identify the bottlenecks to scale. But the bottlenecks can also have impact later on the emulation. So if we run software and the emulation lags behind the actual time or sets wrong conditions, the software and the satellites or the containers would experience conditions that are not real, that are deviating from those they would experience in the real physical environment. So we have to find these bottlenecks to find out where we have to tune the emulation, the platform. And we want to run constellations over a longer period of time, so we have to make sure the whole thing runs stable enough so we don't have to start over again every 2 days. The last one, we were pretty confident this works, but we would have to confirm, of course, that the network topologies can be really, there are no restrictions to the topologies we want to emulate. And that's basically the introduction.
So, yes, I want to a little bit discuss what we did technically. So what I present here is really something like only 1 or 2 small points out of a really big bunch of different problems we run in. To show this, this is something like our, yes, we will get an idea that this is our lab. So we have 3 a little bit more old Dell servers here on this side, where we have 4 25 gig for the control and 2 for 25 gig for the data. We have a switch fabric there, and on the other side we have AMD Dells, 3 and they have 2 25 gig to the switches and for the data, for the control, and 2 100 gigs to the data. They have decent kind of RAM, and we used the bonding protocol. Maybe one requirement which was not mentioned until now, we use only IPv6. This is one of the things we're going for. And we have the goal to have already 100% automation. So the idea is really to roll it out, to roll our setup out, experiment with it, and then if we run into a problem, we can maybe change things. And if we did find some problems or solve some problems, we did it again and build up on top. So installation. So really basics. Installation of the hardware, bare metal installation. We try typically master from canonical Ubuntu here, but this kind of didn't work because it's really not, let me say, that stable with IPv6. We tried it, so we had something like problems with vanishing IP addresses. The API was really not good. This documented. It might be a really good product, but the documentation is a little bit not that good. The next one was to use Cube. I think most of you know that there is some irony behind it, but this even just didn't work. So to get something like, for example, an IP6 configuration, I configured everything, run it, and it created completely wrong configurations for IP6. So completely, it's just, for me it looks that nobody really ever did it before. So there was something like an issue there. And I think it was something like half a year, so there was even no reaction on this. So it's a little bit like strange to me, so strange to follow. What we then did is something like, let me say, a small handcrafted installation, and this is also something like where OpenStack comes in, because we use this image builder. So what we did is something like, we had really something like going back to the basics. So use something like DHCP, having something like the first one, so it's with its server, acts with DHCP, then it gets something like the address, the kernel back, and then the kernel is transferred, the image parameter is transferred. Then you have something like here, a small script is executed on the server itself, which prepares the root disk, and then get the root image and just release it to the disk. So this is something like a really simple way to use about, it's not really that hard. So we have about 3, 4, 5 standard programs, and we have mostly about 100 lines of configuration. So it's mostly straightforward and it works kind of. What we did is, for the disk image builder, I built here this image in the FramFS with a special scripts in, and also this image was built, this image builder. So that it can really just, could be just directly written to the disk. So it's something like with UEFI boot and everything is in, the partition is in and everything is in. Okay. Then I started this one, and what happens was this. so I personally never saw this before. This is really the BIOS crash. So this was from Dell, so I contacted Dell, what they said to this, and yes, it's a bug. So it's really something like it's just really something like the standard DHCP server, just everything standard, added exactly the documented keys and values there, and this happened. So what was there? So they took about 3 or 4 weeks to really finalize it, to finish it, so we get something like in the BIOS update there. Yes, and then there was something like maybe an exchange also with Dell. So they didn't have any documentation how to boot their systems using IPv6. They didn't have. So, and now they have, and they, for example, asked me to review it, and now they can. So they have now the documentation there. Just to let you know, so this was not the only BIOS bug. There's still another one. So, for example, if you really want to see also this kind of thing, if you have, for example, this escape sequence in BIOS is currently not working. So, if you want to see something like this, you can maybe add at the end something like %. Then it's getting in. So this one is a little bit another bug, but it's still not. This is still not fixed. We found it also in this kind of stuff. Okay. This was, let me say, this was one of the spotlights. These are all the things we run into, let me say, going up into the stack. So we don't have the time to go really into all of the things. Maybe one of the things I just mentioned here is the multicast listener discovery. So we use these Dell switches, and these Dell switches have something like DDoS prevention configuration. So what happens here is really for this kind of stuff, you get about sometimes some packets through. So what happens is it starts booting, and then at some point it just stops. And this is really hard to find. And there we had also some support from Dell really to help us debugging this problem. Okay, BIOS bug fix, I already stated this. Okay, then there were a lot of other things. So for example, which I never thought about, dynodify limits do not work for these kind of thousands of interfaces. So you have to increase this by kernel parameters. Then the let me say the IP6R table. So we have to really to increase this to whatsoever. So we have about 60,000. Yes, we have 6 servers. So we have about 60,000 IP addresses. So IP addresses up addresses here, and we have really to increase this. Socket buffer sizes did not work. Then there is, for example, one configuration parameter that states how many packages are processed in one cycle of the kernel. So it's just something like foil sometimes, and then it processes like 100 or 1,000 or 10,000 of packages, and we need to increase this also. Then we had to set the transmit hash policy, because this was the only way we could have this bonding working, that it really uses both interfaces. Then it was something like CNIs. So we tested with a couple of different CNIs to have the first IP address provided, but we started it, and it was very promising, and after 1,000 or 2,000 or 5,000 it just stopped, because if you have something like an IP address manager, which is central, it's just overwhelming. So it just cannot handle all these requests and responses. So what we did is here, for example, we used ipvlan to have something like global IP addresses then. So you see, so okay, of course, this was the easiest part. So the standard has the configuration parameter from kernel, from Kubernetes, it's about 110, and we increase it to, let me say, down, I think 5,000 or so, but we didn't reach this level now. Then NIC limitation, this was another point. So this was also new to me, because we have really up-to-date NIC cards, but also they are not capable of handling these many MAC addresses. So there was something like overflows in the MAC address table of the NIC cards. Okay, and of course the L2 switches, the L2 MAC entries and the switches has to be increased, because they, by standard, they could not handle that much. And of course, what we also ran, what we tried, we used the exhaustion, but this didn't work at all, because we have something like an exploding network, because one package is sent to all of the other ones. So these are, let me say, yes, most of the things we explored, and most of the things we had really something like either solutions or even workarounds. But after this, so it took about 2-3 months or so really work. We found something like a stable setup now, where we have running about 2,000 pods on one worker node, and each of the pods has about 5 interfaces. So we have one with the primary interface, and then we have 4 Multus interfaces in addition. So we have per pod about 5 interfaces, and this works and this runs.
I think it was a little bit more than 3 months if we include the resolution time for the bugs.
Yeah. Okay, so what we did is really something like a current state. We have completed, automated everything, so we have really something like also in CI/CD. So if we update things in this lower level, everything is installed from scratch. We have this Ansible playbook, which is really something like also this which configures the complete stack. Already mentioned this interfaces. The startup time is about 3 hours, so it really takes time. And what we have something like is the base load. So on each container, there's something like it by random has a count, uses an IP address, and then it links to it. So in each container, one thing is running into different IP addresses. And we have something like additional measurements with IPAM. This is really stable, so we run it for about 3 months or so, and without any problems. What we did, we tried to increase it more, but then we run into other problems which we don't have any time to solve. And as of now, currently, this is for us enough. Maybe somebody is really interested in increasing it, then we invite it. Yes.
Quick question: is the parallel things, are they ICMP things or some other kind?
ICMP things. Okay, and I think this is not good.
Then to wrap it up shortly, in future, obviously, as Andreas already mentioned, we want to increase the performance if possible, but for the time being, the scaling is sufficient for the network simulations or the topology emulations we have in mind. What we will have to work on is the fidelity of topology emulations, because in some cases we see that commands are lagging a little bit, and that has impact on the changes of the topology, and thus on the software we run inside the containers. We're also currently working on creating a simulator that can load satellite data from NORAD or NASA and simulate the positions of satellites to define which ones have line of sight conditions, can create links, create network filter tables and TC rules out of that, and feed it into the simulation. So we can download, it's called TLE data, basically satellite positioning data, and feed the resulting topology directly into the emulation. And of course, once we have all that, we will start testing existing and developing new protocols. Some colleagues are also thinking about AI. We'll talk these days about AI. And we're also participating in some research projects. So if somebody wants to participate on what level ever, we're here for discussion. And if you have any questions, then go ahead.
So you mentioned that one of the problems you had to work around was the limit of MAC address in the NIC.
Yep.
How did you work around that?
Honestly, you can just switch them off, and then everything is done in software.
I think you were first.
In your opinion and in your experience, how many probes we can fit inside a node before refusing to use the VXLAN and changing IP address management?
That's a good question. It depends on the VXLAN setup. But, and we did not test it for it. We know that after, I think it was a few hundred pods, it did not work anymore. But we did not test that specifically.
So 200 is enough limit for the configuration.
I think it really also depends how do you set up the VXLAN. So if you use, for example, an external, let me say, external ARP table like an PGP or something like this, then you might get a little bit more, but we didn't use it, so we just used the normal thing, which is something like the Britsch.
Explodes in multicast and
yeah, if you introduce VXLAN, you have also to be careful with the number of bridges you create. There are other limits than behind that. As I said, we did not explore that because we found that it works without it. Thank you very much.
Are you open sourcing this solution in implementation?
Open source, so we didn't write any code. So what we are currently planning is something like having a paper, writing everything down, and this we're currently looking.
Like for example, because you said that you were opening for improvements and partnerings.
Yes.
But you need to first
of course
duplicate your setup so we can build on it.
Yes, of course. So as I said, so we are discussing how to publish the paper, but we currently
the paper is already written. I'm not sure if I get the right order, but let's just start from the left.
You spoke about your your own net boot installation tool. So was it only a one-shot tool, or do you want to make a product with it and maybe opening it, or?
I'm not really sure if this is worth it, because it's really something like the standard things like the HTTP server, the DNS mask, whatsoever. So it's really something like the standard set of how do you boot a server and an HTTP server and disk image spreader. So I'm not really sure if this is really worth
Okay, so it's very classic, just a bunch of scripts and configuration.
Exactly.
Nothing
something
fancy.
like pick the right tools, something like the integration done with about, let me say, some configuration files.
The main part was that IPv6 was not tested apparently.
What kind of test do you run in there? Do you just run normal TCP/IP? Do you have like what kind of workload do you run in there to test to emulate? What do you emulate there?
Now or in future?
What's the plan? Yeah, now and
right now we're just testing if the topology works by using ICMP pings.
Yes.
Later on, the first task will be to validate or to test OSPF and ISIS to check how they handle the huge amount of updates.
So the topology of the network is changing all the time because satellites come in out of sight,
yes.
and it's evolving the routing tables everywhere.
Yes, I mean it's the grace periods are in question. We had a few preliminary tests and we found very strange things like return and forward and return path hop counts started to differ, which means there's some problem somewhere, and we had TTL expirations, but that was just preliminary. That was the first test if the topology works and not the test.
So actually, there's the third question on the same topic regarding the open sourcing the project, regarding the distributing the boot server solution. I'm working right now on the same actually solution, kinda, and I can understand that this experience, this knowledge is really important. It's valuable. So what actually we plan to do, and I would like maybe ask you to do the same thing, to packet it into a container that could be distributable, that people could like download and run in Docker or in Kubernetes. It depends on the CNI, but at least in Docker. So this knowledge would be encapsulated in the container beside of the paper. Because that's the code. It's like the code open source is not like always when you write a C program, but this solution is really important.
Yes, you're right. Maybe
Could be
something
valuable to
like
share.
yes, maybe something like let me say Docker file plus basic configuration.
Yeah. That's what we do. That I could. If it's possible, I would like to ask you.
Of course, we have to get internal approval. We're working for a company. But
Thank you. In advance.
any more questions?
Just an observation. I used to work on the near space network, which is basically service to 2 million clicks out for NASA, and this is very impressive. I just wanted to say that. This is more than we could have dreamed of back when I was working there.
Thanks.
Thank you.
You're welcome.
I was just wondering between when you started the project and kind of managed to get to this point, if there was any sort of different tools, techniques, projects that you kind of wish that you had started with, or you're kind of happy with the whole thing?
On what level? On the Kubernetes scaling level? On the routing level?
Yeah, on either of those.
On Kubernetes, at least I'm not aware of any other project that tries scaling to that level.
No, so what we tried as the first point is, or let me say in parallel, to have something like a minimal setup, like using only namespaces, sort of network namespaces, and run everything inside. But then you have something like limitations, and do you need something like an orchestrator for this one? So we have to see what's ready.
Regarding routing in these dynamic topologies, this is active research. There's a lot of research going on. There are constantly papers published, and there are also some other approaches for simulators or emulators, but they usually don't scale that, and we have some other features which I have not seen there.
You said that the paper is finished. Is there any way we can get our hands on that paper today?
Again, no, not today. Today, not. As I said, we have to get the further approval for publication, of course. Having worked for NASA. Further questions? No? Then, thank you very much.